let's now consider the magnetic force on a charge. Now we're back to charges. So remember, there's no magnetic charge as a source of the magnetic field. There's only dipoles. That's what we were talking about. But the magnetic field still applies a force to a charge. So sources is where there's no magnetic charge, there's only dipoles. But what you do to a charge, that's the idea of the B field. Right? So just like the electric field applies force to a charge, that's really all the magnetic field does. It applies force to a charge. So let's look at the equation then that describes that force. I kind of showed it to you before because I showed you the total force on a charge for E and B. But if we just look at the B part, then it's just Q, the charge, the magnitude, or the charge on the charge. V, it's velocity cross B. That's the equation. If you have a charge moving in a magnetic field at some velocity, this is the force it will experience. The cross product here is a way to multiply vectors we haven't used yet. We've talked about the dot product to get the amount of work something does. It's the force dotted with the displacement, F dot D vector. And that's really how much of these forces along each other, and it gives you a scalar. But there's times when we need to multiply two vectors and get a vector. So that's what the cross product does. It's a way to multiply two vectors and get a vector back. So multiply two vectors and get a vector. But it's also harder than the dot product. You'll see why. We'll look at how it behaves. All right. So now let's just do one. Let's imagine we have a uniform magnetic field this way. So everywhere in space, uniform magnetic field, like we always draw. Okay. And we're going to put a charge in there with charge Q. Let's put it right here. And we're going to have it moving down with velocity v. In this case, at 90 degrees to the magnetic field. Okay. So we got to think about which way is the force going to be and what's its magnitude going to be. So we want to think about what is this equation telling us. So let's do the magnitude first. The magnitude is simply Q. That's just a scalar number. The magnitude of the velocity, the magnitude of the B field, times the sine of the angle between them, not the cosine. So there's theta. It doesn't have to be 90 degrees. I drew it as 90 degrees. But it's Q VB sine theta. So dot product is maximum when they're aligned, but cross product is the opposite. It's maximum when they are perpendicular to each other. So if V is perpendicular to B, that's when you get your maximum magnitude. If V is parallel to B, that's when you get 0. So in that sense, it's like the opposite of the dot product. But then what about the direction? So you get the direction from the right-hand rule. You just say V, in this case, V cross with B, and it points out. So in this kind of work, and you get to the magnetic field, 3D becomes very important. Okay? So in the electric field, it had to be 3D. You had the fields and you had to think about the flux. It had to be 3D. But most of the drawings you could get away with 2D, and you could just kind of visualize it in 3D. Right? Magnetic field, we don't have that option. Okay? So here, the direction is from the right-hand rule, and we are going to have to draw it out of the board. We have no choice. So what you really have to think about is treat the vector really as an arrow. Okay? So if I were to draw the vector arrow like a real arrow, it's a stick, right? And then you make a little arrowhead out of wood, right? It's got the little part. You found one when you were camping, and they use a little twine to tie it to the stick. And here there's some bird feathers out here, right? So we have to, think about a real arrow. Okay? Now, if that vector arrow is coming at you, what do you see? You see the tip of the arrow. So this is how we draw a vector out of the board. Okay? And if instead of the arrow coming at you, it's going away from you, maybe you shot the arrow, then you see the feathers. So then we draw an X. Okay? Those are the feathers going away from you. That's going in to the page or to the board or wherever this is printed. Because in magnetic field, everything is always three-dimensional because the B field and the velocity direction make a plane, and then the force is always perpendicular to that plane. So there's just no way to do little approximate 2D drawings. So if I was going to draw this force on this charge, I would probably draw it kind of right next to it, and it would be a circle with a dot, because the right-hand rule made it point out. So there it is. You get the magnitude, QVB, sine theta, where that was this angle, and then you get the direction from the right-hand rule. Okay. And I see, oh, we have a question. Let's see here. We've got, where'd the question go? There, oh, friends of P, right-hand what? Oh yes, the right-hand rule. You're going to have to be very good at the right-hand rule. So to understand anything about magnetism requires constant use of the right-hand rule. It's a way to use your hand to figure out what direction something's going to be. So why don't we'll take a break and we'll think about the right-hand rule for a little bit.